The time has come to talk about time. No, that's not good. Not good. Oh, you're late. It's about time. I hope your schedule's free because this is going to take some time. What time is it? It's science time. This is taking too much time. Chapter 5, what is time? In this chapter, we are going to take the dimensional concepts we've been building on to answer the question, what is time? This answer will include the following. Why does time only move forward? Why does time move at different rates depending on speed or velocity? Here's a fun one. Why inertia is a property of time. The relationship between C and time. A better answer to the twin paradox. I'm looking forward to that one. Can we time travel? Spoilers, no, but the fun part is why. What anti-gravity really is, why wormholes don't exist, and how understanding time as a dimension will enable us to travel faster than light. Now, it should go without saying, this is called Chapter 5 for a reason. It follows chapters 1 through 4, which I did in a previous video. It is linked to below in the description. If you don't have the patience to go and watch that video before watching this one, at least please be aware that we will cover several things that probably won't make any sense to you at all, especially an extra fourth spatial dimension we labeled W from our last video. However, I can't stop you, so feel free to watch this one, but please go watch the other one before leaving me confused comments. After my last video, a lot of people have expressed some incredulity that someone who seems to have spent their life mostly in marketing is doing a video on science. That's right, for those of you who didn't look it up, marketing's my day job. But I do think I really have something to offer here, not just on the science side, but because I'm going to tell you that part of the problem we've had with physics and understanding the world around us is a branding problem, or at the very least, a semantic problem. The language that we use to talk about time greatly influences our thinking of what time is. And when we bring all of that baggage into science with us, it leads us to some really strange conclusions. Time has become a kind of conceptual spaghetti that prevents us from really honing in on it and figuring out what exactly it is. And if there is something I am traditionally qualified to address, it is language, semantics, and the science of perception. So, before we get to the physics of time, we're going to take a minute to visit my other video format to address the language of time. Chris, take it away. See, it's a different shirt, different time. Closing time! Hello, and welcome to Words Matter. This is the show where we talk about words and how we abuse them. Today's word is time. Time is a word central to the human experience. But because of that, time is both a practical word, but also a form of expression and communication. We attach emotions to it, feelings. For example, you are wasting my time. I had a really great time. I don't have the time for this. Well, it's about time. That was well worth the time. How many times do I have to tell you? As you can see, time lives in our head in a way that's analogous to a feeling or even a resource like food or money or even energy. But even when we use the word time in more practical ways, time works as a catch-all for many different concepts. We think of history as time, like the classic sophomore debate, if you could go back in time and kill baby Hitler, would you? Oh, look at him, he's so cute. Wait a minute, babies can't grow mustaches. We assign our memories as a measure of time. For example, I remember it like it was yesterday. As we try to ponder or predict things that will happen, we assign that to time. I don't think that's going to happen for some time. We even assign an element of luck to time. Boy, you made it right in the nick of time. Or, hey, your timing on that was really lucky. The way we think about time is also influenced by our culture. For example, here in the West, we think of the future as in front of us and the past as behind us. But in some cultures, the future is behind you because you can't see it, and the past is in front of you because you can see it and remember what happened, for most of us. In some cultures, remembering the past is important or even sacred. And in other cultures, letting go of the past and forgetting about the past is the key to inner peace or spiritual freedom. And in some cultures, the goal of a healthy mental and spiritual life is to always be present in the moment. Some of us live entirely in the future, thinking only about tomorrow, or what's going to happen next, or what we'll get someday, or, sitting at our desk for years and years just pondering retirement. How we perceive time depends on our values, our culture, our background, our language, and our upbringing. For example, in American culture, we even like to say time is money. The truth is, even scientists have fallen into this trap around time. In discussions about what time is and how time works, they've often struggled to isolate what the meaning of time is. And I don't mean the meaning of time like, what's the meaning of time? I mean the definition they're applying to time when they talk about it. For example, there is the expression, the arrow of time, where we assume time is traveling in a straight line forward from the past to the present to the future. Some physicists think time is defined by entropy because it's a predictable pattern, a physical phenomenon that we can predict. We know what's going to happen with certain things over time. Another principle we assign to time is causality. The fact that certain things can only happen if they're caused by other things, and those things have to happen in a strict sequence. One thing causes another. Another property that we assign to time is the idea of a timeline. The idea that everything that's ever happened is somehow recorded on a mystical string of causality that just continues through the universe, that we can hop back at any point. And this assumption is so strong, it's the basis for most of our sci-fi TV shows and movies. A plot line, by the way, I am incredibly tired of. But we use time, most importantly and most tangibly, as a form of measurement. There are so many things that we compare to and measure against time. And that's what makes it just feel so tangible and so real. But the biggest mystery in science, however, is that we have learned that time is relative and it changes from perspective to perspective. And that is very confusing. So, if someone were to have an in-depth discussion of time, let's say relating to a scientific theory, I would begin by asking the question, what time are we talking about? The answer to that question is beyond my purview. After all, I'm just a cunning linguist. I will leave that question to the other Chris, who is currently pretending to be a scientist. So, that's it today for Words Matter, and remember, always try to use words good. Back to you, Chris. Thanks, Chris, I think. So, like Chris said, we're going to start this video by narrowing down the definitions we're going to use on time for most of the presentation. So let me take a minute to define what we're talking about. We are going to refer to time under the following definitions. It is a form of measurement by which we compare relative motion. It is a dimension, and we're going to include in that definition the concept of causality, one thing having to happen before another. So all that stuff you just heard the other Chris talk about, I want you to take all that and put it in a bucket, and we'll get to that later. To begin answering the question, what is time? Let's take a minute and revisit what we know about time. So just like in the last video, we're going to start by reviewing what is accepted science today, and we're going to have the return of the labeling system. So you can see as we flip between accepted science, where again, I'm just telling you what is currently accepted science. Please don't argue with me about the accepted science part. In the comments, take that up with academia. And then we will switch to the science theory part, or the part where I'm bringing my hypothesis to this, okay? So keep your eye on that. Okay, current science concept number 1. Time is relative. Time is always measured relative to something else. For example, we measure days by the Earth turning. And we break days up into hours, hours into minutes, minutes into seconds, which we then do things like set our clocks by and set our watches by, and we use gears to track that. We measure years by the Earth's orbit around the sun, and we use that to create calendars and dates and all those kind of things. All of this time is dependent on the relative motion of other objects. Even a gearless watch uses oscillating crystals to keep track of time. There's no way to track time without something moving. Point number 2, time changes with velocity. This is one of the main consequences of special relativity, but should be noted to a certain extent already existed with Galilean relativity. The faster we move through space, the slower we move through time. The slower we move through space, the faster we move through time. This relationship is one of the core principles of modern-day physics. This has led some scientists to think that if something is traveling the speed of light, it then would experience no time at all. But we'll get to that later. Point number 3, objects at different speeds experience time differently. So this is very related to the point number 2. But this relationship is shown in what we call the Minkowski spacetime diagram. We covered this a bit in the last video and in the Minkowski spacetime equation. If you remember from the first video, the purpose of the graph and the equation is to help us measure if two events can influence each other. So that's causality. We measure their space-time distance, which isn't just how far apart they are, but based on their motion and their movement in relationship to each other, is there enough time for one event to influence the other, even if it was moving at the speed of light? It also helps us calculate time dilation. So this brings us to the twin paradox, one of the most discussed thought experiments when it comes to special relativity. Lots of videos on YouTube about it. And for those of you who may not know, here's a little bit about how it works. We're going to have two people starting at the same place. One person is going to travel in a spaceship from Earth to the nearest star, a distance of about 4 light years away, at a speed of about 80% the speed of light. During this trip, each of these people have incredibly powerful telescopes with amazing powers. Just follow along, please. Don't get too picky here. And the point is they can each see each other during the trip, okay? As the person looks out from the spaceship to the person on Earth, they appear to be moving faster, while the person on Earth, looking at a telescope to the person in the spaceship, they appear to be moving slower. I don't mean the spaceship, I mean the person in the spaceship. They appear to be moving a little bit in slow motion. To the person staying on Earth in mission control, to them, this trip is going to take about 10 years. However, the amount of time as measured on the ship's clocks and the aging of the travelers during their trip will be reduced by a factor according to the Lorentz transformation. So because they're traveling 80% speed of light, the trip takes 6 years for them, but it appears to take 10 years on Earth. So bottom line, when the rocket ship gets back to Earth, the person rocket ship has only aged 6 years, but the person on Earth has aged 10 years and looks a bit older. It was a very stressful 10 years. Now, this mental experiment is something we have confirmed. It is tested. We know that this effect happens. Now, obviously, we haven't tested it by traveling to a star, but we've tested it on smaller scales. If this concept is new to you or you're feeling incredulous, please look in the description, as I have videos that go in much more detail on special relativity and the twin paradox. The point of me bringing it up in this video and covering it again is to point out a couple things, but the first one we're going to start out with is a problem with this mental experiment that I've never seen anyone address, and it stuck out to me like a sore thumb since high school, and that is, they can see each other. Hold on, just think about that for a minute. The man who has only traveled 6 years and the man who traveled only 10 years, they can see each other. Now, this is not the paradox, or the official paradox of the twin paradox. We'll get to that later. Don't worry, I'll cover it. But this, to me, is the more interesting problem, because that is not how we think of time. With our current understanding of time, and we often use the phrase a timeline, a concept of a timeline, which is pervasive in our culture, we can't see people in the past or in the future. For example, Abraham Lincoln, he's in the past. I can't see him, not without a shovel. Every idea of time travel we have means the person is traveling along the timeline. You see this in Back to the Future. You see this in Doctor Who. You see this in Marvel movies. Don't even get me started on Marvel movies. People who travel to the past disappear because they're leaving this point in time and they're going back in the past to another point in time. And then, hopefully, if they make it back, come on, Doc Marty, you can do it, they magically reappear. Our perception of time, the idea of time that we have in our heads, is a sequence of simultaneous events. That's why when we think time travel, we go from one simultaneous sequence of events to another simultaneous sequence of events. But as you can plainly see from the twin paradox, and again, experimental proof, that's not what happens. Someone in one frame of time and someone in another frame of time, they're just both in the present. There is no timeline. As you can see from this picture, if we were thinking as a traditional timeline, the person in the rocket ship who only experienced 6 years of time passing for them, they would be at the 6-year point on the timeline. The person on Earth who experienced 10 years, they'd be at the 10-year point of the timeline. The person at the 10-year point of the timeline would have to wait 4 years to see the person in a rocket ship. But again, that's not what happens. The guy in the rocket ship comes back and makes the other one feel really terrible about being 10 years older. So, our idea of the past looks like this.
All you have to do is drive the time vehicle directly toward that screen, accelerating 88 miles an hour.
Wait a minute, Doc. If I drive straight towards the screen, I'm going to crash into those Indians.
Marty, you're not thinking fourth dimensionally. They'll instantly be transported to 1885, and those Indians won't even be there.
Right.
This is a memory we have of a sequence of simultaneous events. However, in physics, the past is something that we only see from the leftover remnants. So theoretically, an alien in a distant galaxy could, many, many years in the future, watch Back to the Future on his television and be looking directly into our past, in which case he would know we don't understand physics. So again, this is not the official paradox of the twin paradox, but I think it's a much more interesting problem with it, because it points out that our idea of time is based on memory. It's a function of how our brains process the world into past, present, and future. But relative time is about motion and causality, and that's what we're really looking at in physics. And this is why science has a semantic conceptual problem, because it keeps confusing the abstract idea of time with the physics idea of time. And by the way, I don't know what to do with the label down here. It might cause a bit of commotion, because what I'm telling you is still within the realm of accepted science, and yet at the same time, the spin I'm adding on it is not. But it doesn't violate anything in physics. In fact, I think it describes physics more accurately right now. I'm not even adding much new to anything, if anything at all. So, whatever, it's just going to have to figure it out. Point number 4. Geometrically speaking, relative time forms a hyperbolic relationship with space, especially when we try to represent it in a two-dimensional graph. This may seem overly technical at this point, but trust me, this is extremely important to not only understanding time, but understanding why we are confused about time. As we mentioned in the Minkowski space-time diagram, the way it works is we take the traditional 3 dimensions of space, x, y, z, and we compress them down to just one line that forms the x-axis of the graph, and the y-axis is normally labeled t or ct, which is time. When we map the world lines of an object traveling through space-time, that relationship forms on this graph a curve. Whereas on a normal graph, between two perpendicular dimensions, we would have normally more of a linear relationship. This phenomenon, we already did that joke. We already did that joke. This phenomenon, damn it, this relationship on the graph is what we call hyperbolic. So let me explain what that means, and bear with me because I'm going to use kind of my own terminology for this, okay? The three familiar dimensions, x, y, and z, they all work the same way. They are additive. They stack on each other, just in completely linear mathematics. And they're interchangeable. So here's what I mean by that. If I take a three-dimensional cube, there we are, a couple things here. First of all, I can travel through all three of these dimensions at once. I can start at the bottom back of the cube and come to the opposite side on the front. Now, I'm traveling in a straight line, but I'm traveling through all three dimensions of the cube. I cross all three planes. Now, the other thing is you see the labels x, y, and z. I can mix these up. I can move x and y and z around anywhere I want to, and it just means the same thing. It's arbitrary, really, which one I label x, y, and z. So they're interchangeable. Traditionally, this is what we call a perpendicular relationship. Each one is 90 degrees relationship to the other. I can move through all of them at once, or a few of them, depending on how I'm moving, but the movement can be simultaneous. The dimension of time, on the other hand, is subtractive. It's mutually exclusive. The more I move through space, the less I move through time. The more I move through time, the less I move through space. The phenomenon of this, damn it, this weird thing that happens is shown in the equation for general relativity with the metric tensor. So here's the metric tensor. Not explaining how it works right now. We talked a little bit more about that in the last video, and I have videos below if this is new to you. But in the metric tensor, this is basically a grid representing space-time. And you can see the x, y, and z, they have a 1 as kind of the default in each of their columns, while the time has a -1. This is how we imply the inverse relationship in mathematics. So to drive home this point, I'm going to show you a graph of a 2D circle and a 4D circle represented on 2D. And here's what they look like. Now, as you can see from the 2D circle, if I'm charting, again, the world line, velocity through space, I can have the same size going from the center to the edge, and all the lines are the same length. However, on a 4D circle, as I take those same lines and map them on space-time, these lines are actually all the same length in 4D, but in 2D, they're warped, looking like they're longer than each of the other. Again, the actual math for this, I have descriptions for in the video. I'm just trying to get the concept of hyperbolic across here at the moment. Side note, I'm pretty sure my bathroom mirror is 4-dimensional. Anytime we try to represent extra dimensions and fewer dimensions, we get this warping effect. You see this most commonly, in everyday life on a picture of the Earth, where we're taking a 3D object. So the Earth is a 3-dimensional, mostly round ball, and we stretch it out flat to fit on 2D. And of course, the problem with these 2-dimensional maps is that almost everything is actually the wrong size in relationship to the other. So in other words, the lines that I just previously told you were the same length, but they look like different lengths, well, that's caused by the same thing that causes these countries on this map to be the wrong size. So one more illustration is to drive this point home. If I were to draw a straight line on this map from New York to Paris, you would think, hey, that must be the shortest distance between these 2 points, but it's actually not. If I take this map and bring it back into a globe, now I'm going to draw the real shortest distance between New York and Paris, and you can see the difference for yourself. So the reason I'm bringing this up is because hyperbole has a major communication problem, and it plagues science even today when we're dealing with extra dimensions. So the first problem hyperbole causes is that the visual of the object never matches the containing space of an object, and the path of an object in hyperbolic space can be perceived as both curved or straight, depending on how it's represented. I say this to say the hyperbolic path of an object in space is not an accurate representation of the space it's actually in. I know this is a hard concept to get. Let me just try one more illustration. So let's just take the Earth. It's a round ball in 3 dimensions, okay? Again, if I were to chart, as I just showed you, the shortest distance between 2 points, that would be curved. But the containing space of Earth is flat. So here I have Earth inside of a box that's just showing the dimensions of space. These, as far as we know, these dimensions are flat, x, y, and z, and they go infinite in both directions on their dimension. So the best way to represent the space the Earth is in is flat, even though the Earth is round. And this goes back to one of the dimensional concepts I talked about in my last video, that when we're talking about extra dimensions, we could be talking about either an object or the containing space the object is in. All right, if you're having trouble getting your head around hyperbole, I'm just going to show you a wonderful clip here by Code Parade, where they kind of showed what a 4D hypersphere would look like. We'll play that.
So take a guess what happens on a hyperbolic walk. We'll walk up 1 tile, right 1 tile, down 1 tile, left 1 tile, and finally up 1 more time. Now we've walked on a pentagon with 5 right angles.
But here's the thing, that is what a hyperbolic object would look like, not necessarily the containing space it's in. So, to some of you, it might seem like this is extremely basic or a no duh. Just know that I'm covering this because this is going to play a key role in our fundamental misunderstanding of physics and time. And this brings us to point number 5. Time is a limited dimension. So x, y, and z, as far as we know, they're infinite. We have no way to know where they end, and as far as we know, they go on forever. But time is limited to roughly 300 million meters per second. So again, for a reminder, if you remember from our last video, c is not actually the speed of light, it's more the thing that limits the speed of light. C is the fastest any 2 events can happen. We use the Minkowski spacetime equation to determine if 2 events are too far apart to influence each other, and that's what C is for. All right, so now that we've covered all the accepted science, let's get to the fun stuff. What is time? Time is a physical, spatial, geometric dimension that makes up one of the containing sides of the universe. It just happens to be so different from the ones that we're very familiar with that we've failed to acknowledge it as such. By understanding the true geometric nature of time, we will be able to have not just a lot more clarity, but uncover a whole new world of physics. So what I want to do now, for a little bit moving forward, is I want to help you conceptualize the shape of time. So please understand as we go, I am trying to communicate a dimensional concept, a kind of visualization of geometry that, depending on the person, can be extremely difficult to communicate. It's like trying to explain to someone who's colorblind, what blue looks like. So we're going to use a lot of different analogies. I'm going to try to tackle this from a lot of different directions. But please keep in mind the expression, every analogy is flawed, but hopefully they are useful. So every analogy we have here is going to be for the point of pointing to a specific reality of time, but none of them by themselves really hit the nail on the head. Or as Bruce Lee said,
it is like a finger pointing away to the moon. Don't concentrate on the finger or you will miss all that heavenly glory.
All right, so first of all, let me define what I mean by when I say time is a dimension. I mean it is a direction of motion which affects the final calculated vector of an object. So in this case, Minkowski spacetime is part of the calculation we can use, although in general relativity that gets more complicated, breaking into things like Christoffel symbols and all that. I consider anything a dimension that we can observe or measure by relative time or motion. And I mean it's a dimension in that it is part of the containing shape of the universe. So if you remember from my first video, I titled this theory I'm working on, at least so far, The Unifying Theory of Dimensional Geometry and Interaction. As I said, I'm still kind of working on that. But the point is, I'm trying to propose a different way to think about geometry that clarifies some of the concepts we're seeing in math. And by the way, just as a note, I am not calling this a unified theory. It's not a theory of everything. My only goal in this is to marry general relativity and quantum mechanics. When I get there, trust me, it will not explain everything in the whole world. So, to understand the shape of time, we're going to start by making up a word. Again, marketing guy here, I can do that. So, the word we're going to make up is contradicular. Now, I'm going to use the word contradicular to define the angle at which time sits to the other dimensions of space we currently have. And I'm making up this word because we've never made a word for this angle in geometry because we've just been calling it time. But if we're going to understand things geometrically, we have to come up with an objective way to describe it. So, perpendicular means at a right angle to. We call a dimension perpendicular if it is at a 90-degree angle to all previous dimensions. Again, that's x, y, and z. And perpendicular dimensions are not mutually exclusive to motion. You can move through all of them at the same time, move around circles, all sorts of stuff. Doesn't subtract. Contradicular, however, it's still at a right angle, but somehow it's inverted. So the motion of a contradicular angle is mutually exclusive. The more you move in one, the less you move in the other. Again, this is why in math equations and everything, the dimension of time is represented either by -1 or 1 divided by. Either way, we're always inverting it compared to the other dimensions. In understanding the shape of time, if you remember back to my first video, I talked about the concept of an ant farm dimension, that a dimension can be limited and yet everywhere at once at the same time. Time is our ant farm dimension. It's another reason why we failed to recognize it as a dimension, because all of our other dimensions are infinite, but time is limited. Now, I know it's hard mentally to conceive of a dimension that is everywhere at once and yet limited. So if you want to go back to my first video, that may help with some of the concepts. But if it also helps, again, in the last video I talked about a fourth spatial dimension, which we'll get to again in this video to tie it together. But think about how weird that one was, as it was kind of a way of compressing or growing the existing 3 dimensions on top of each other. And if that one was weird, then think about how weird these dimensions are going to get the more higher up we go. So give your mind a little bit of room, to not necessarily get it all the way. I will do my best to make it tangible and measurable. As a reminder, for the Minkowski diagram, again, x, y, and z, these dimensions are additive. So even though they're all perpendicular to each other, when we make a Minkowski space-time diagram, we're actually representing them as perpendicular. So here's kind of how that looks. I have x, y, and z all stacked on each other. I'm throwing in w for my last video, and I have an asterisk on it. We'll get to that later. And then as you can see, time is perpendicular to all of those. And then as we get to the space-time diagram, we're just going to compress all of those down into a single axis and have time as the only one left that's perpendicular. So as you can see, it looks something like this. All the perpendicular dimensions squunched together into one x-axis, and now time, being shown perpendicular to all of those, is the y-axis. And we have a line going from time down to space, showing that the more we travel through time, the less we travel through space, and the more we travel through space, the less we travel through time. Now, the problem with this diagram is that this shows a linear relationship. And as I said, time forms a hyperbolic one. So this, as an object, would travel between time and space. Its path would actually look more like this, curved in a very dramatic slope. And it's that slope that gives us the idea that space-time is curved. And I will address why that happens a little later. For now, I just wanted to show an accurate depiction of the path of an object in its relationship to time and space, because I have to refer to it as we go. It is the nature of time being at a contradicular angle to the other dimensions that enables motion to begin with. In fact, motion and time are pretty much the same thing. To show you how this works, what we're going to do is we're going to take the Minkowski spacetime diagram, and we're going to flatten it down and make it a circle, with time being the line from the center to the outside, and with space being the circle around it. Representing the object moving, we have the cute little robot Greenwich. Greenwich is starting at the top of the time axis, in this case, the center of the circle. Since she is experiencing the maximum amount of time, everything is moving around her very quickly. So as you can see, though, the objects closest to Greenwich are moving slower, and as the objects travel farther and farther away from time, they're going faster and faster. Because the closer they get to the edge, the closer they're moving to the speed of light, which, as we said, many people think means you don't experience any time at all, but we'll get to that. So as Greenwich moves from the center of the circle, which again is the top of the y-axis here, to about 80% the c, or the speed of light, moving through space, we're going to see that the objects around the same speed as her look like they're standing still. The objects that are back up on the time axis are moving now backwards to her. Her experience of time has now fundamentally changed. And to a lot of the things that she's matching the same speed with, it seems like nothing's moving at all. By the way, if you're really having trouble picturing this in your head, stop listening to this through audio only, rewind it a few seconds, and please look at the visual. Some of my listeners were not watching it, they were just listening. Now, we'll get to this more later, but what I really want you to notice here is that the dimension of time is not moving in this illustration. It is only Greenwich who's moving between the two different axes relative to everything else. Okay, so now that we've had that look, and we are thinking about time as, again, a part of the containing shape of the universe, now we can move on to look at one of the most fascinating parts of physics, which is inertia. Inertia is one of those things that has stuck in my mind since I first learned about it in physics back in high school. It's the idea that in the vacuum of space, an object in motion stays in motion. And in fact, an inertial frame of reference is a core foundation of the principles of general relativity. Here on Earth, everything takes energy to move, and it takes energy to maintain motion. But out in the void of space, no matter how fast something is going, unless another force acts on it, it's just going to keep going. So it creates this riddle, because we are seeing things move with no energy, or at least no energy once they get to that point. So something I've just never seen anyone really talk about is why. Why is it that something can go any speed, obviously under the speed of light, but it can be going 5,000 miles per hour, it can be 100,000 miles per hour. As long as it's in the vacuum of space, it can just keep going. And that's just fascinating. But if we understand time, again, as another side to the shape of the universe, the answer becomes completely clear as to why that happens. The truth of the matter is, energy is only required for change. And while to us, motion feels like change, it's certainly here on Earth. But in the vacuum of space, the truth is, even though something seems to be moving, at least according to relative motion, the truth is that in the geometry of the universe, it's actually standing still. For example, if we go back to our graph here with time and space, you can see that no matter where an object is, if it is moving 500,000 miles per hour or just 500 miles per hour, while the different changing speed changes its position relative to those two dimensions, holding that speed means it's standing still relative to those dimensions. As Greenwich showed us, she had to turn on her rockets. It took energy to move down the time axis into space. But if she's standing still on the time axis, it doesn't take any more energy. And moving along the time axis is what we call acceleration. That is, in essence, the only thing that changes. Acceleration moves you along the intersections of time and space. Okay, quick interruption here on inertia. I can't believe I forgot about this when we shot it. But conservation of energy. If inertia can be perceived as just standing still relative to contradicular dimensions, then energy is conserved with what we see as motion. If we just keep calling inertia as a property of matter, then it's magic. It's not physical. And just adding to the rest of this discussion on time, if there is a physical past, present, and future, then the universe is constantly having to produce massive amounts of energy. Same problem with the multiverse, of course. But if the present is the only thing that's physical, then energy is conserved. Frankly, I'm not just mad at myself for forgetting this little side point, but I don't understand how this just isn't obvious in physics as a whole. Sorry, interrupt myself. Moving on. This idea of inertia simply being a state of rest moving between the dimensions of time and space is actually very similar to an old idea called Mach's principle. Ernst Mach, in the late 1800s, postulated the theory that local physical laws are determined by the large-scale structures of the universe. And I have to read this to you because it's very hard to paraphrase. You are standing in a field looking at the stars. Your arms are resting freely at your side, and you see that the distant stars are not moving. Now, start spinning. The stars are whirling around you, and your arms are pulled away from your body. Why should your arms be pulled away when the stars are whirling? Why should they be dangling freely when the stars don't move? He was noticing that there's this relationship between how we move and then how we observe the stars very far away moving, and he noticed a connection. And while it's almost more poetic than scientific, this was one of the inspirations for Einstein for the theory of general relativity. And what my point earlier with Greenwich's voyage through time was to actually show that exact same idea, just doing it in a Minkowski spacetime graph instead of in a field. Where Mach is attributing inertia to the existence of relative objects throughout the universe, what I'm saying here is that inertia is attributed by being relative to the universe itself. So with this in mind, let's revisit our definition of time. What we call time in physics is not what we call time in daily life. And again, that's because what we refer to often as time in daily life is defined by our experiences, not by what we can measure. What we are measuring in physics is we are just measuring relative motion from different dimensional perspectives. Past, present, future, they're concepts in our mind, but we don't necessarily have a lot of evidence that the universe sees it the same way. Remember, our minds are pattern-finding machines, and they're designed for survival. So they're almost looking at the world through that pattern-finding mechanism. The things that happened in the past form patterns in our mind that then help us anticipate things that happen in the future.
You are too concerned with what was and what will be. There's a saying, yesterday is history, tomorrow is a mystery, but today is a gift. That is why it is called the present.
And this is a survival mechanism. But it is ultimately a mechanism that's developed to manage the world around us. If past and future were perfect, if they were physical, and if our memories were somehow interacting with something real, our memories wouldn't be so faulty. But as it is, our memories are pretty unreliable. Question, Does the Monopoly Man have a monocle? I'll leave that to you. All the ways we experience time are what we actually call in science as an emergent property. This doesn't mean it's not real. It just means it's not physical. There are a lot of things in this world that are very real that are emergent. One of my favorite example is ants. You take a single ant by itself, and often it just glitches out. It doesn't know what to do. It's like a broken automaton. But ants in a group become almost a single unified thinking organism capable of complex collective effort. That is an emergent system. It's something that if you try to take it apart and examine it, it disappears. It doesn't mean it's not real, and I'm going to try not to get too much into the philosophy of what emergent means. I'm just saying when we're talking about physics, it is important for us to discern what is physical, what is measurable, and what we're actually observing, and be careful not to bring all of our previous assumptions into it. So, everything our brains experience as the flow of time comes from comparing one event to another. We think time has passed because the sun moved, our clocks change, we get hungry, we get tired, we move from place to place. Because the dimension c determines the rate at which these things change, we have mistakenly confused it with all these other meanings of time that we've come up with. But since relative motion is change, and I know I just said more specifically acceleration, but I'm just saying as we observe any motion, the more we move, the less things can change. Since when moving very quickly, things change less, like clocks moving slower or us aging slower, we think less time is passing. But in physics, c is just a rate of change. So moving forward, we're not going to call time anymore. We're just going to call it c. It's the dimension of c. And then we'll circle back later to talk a little more about all the phenomenons of time. All right, so with the idea of c as an actual physical dimension, another side on the containing space of the universe, let's revisit what's the actual paradox of the twin paradox, or the more official paradox. The perceived paradox of the mental experiment is that the way special relativity is taught today, all speed is relative and no point of reference is correct. So all points of reference, they measure it differently and they're all right. Not who's to say which one's better than the other. But this causes a problem because while the person in the rocket ship is traveling 80% the speed of light to the person on Earth, the person on Earth is traveling 80% the speed of light to the person on the rocket ship. So the paradox is what makes the person in the rocket ship age slower and not the person on Earth? How is the universe picking which one of the two is the correct point of reference? Now, if you're like me, back in high school, you're probably thinking, what's the problem here? The guy in the rocket ship aged slower because he's in a rocket ship. And you'd be right. The person on Earth isn't changing speed. This is a paradox that really only arises when you're just neck deep in the theory and the math, and you're just kind of lost all touch with reality. But it does bother a lot of people, so let's answer it in a more sciencey way. There was a recent heated kerfuffle on YouTube where Don Lincoln from Fermilab tried to answer this question, and then later Sabine Hassenfelder also tried to answer it, and they gave seemingly different answers. This led their audience to duke it out online and on forums, as people do. In the end, good old Don released a ceasefire video explaining that while they used different semantics, they were fundamentally saying the same thing. By the way, I'm linking to both in the description. And I really hope you look at those links in the description because I'm very excited about you comparing their explanations to what I'm about to say. In Don's video, the explanation came down to frames of reference. So basically, that the rocket ship has multiple frames of reference compared to the person on Earth because they change direction. They go to the star and they come back. So, and then he also adds a third person frame of reference to kind of act as an umpire near the end of the video. And his argument is basically, since one had more frames of reference than the other, that one is correct. Sabine, on the other hand, said that while speed may be relative, acceleration is absolute. So basically, even though relative speed, they're each moving 80% of the speed of light to each other, the rocket ship is the only one to accelerate. So that makes it the right point of reference. So just to weigh in a little bit before we move forward, Don's answer is actually the one that's more of the textbook-friendly answer. It's the answer you'd probably get from a professor at college or your high school physics teacher. It's the one that's more often used. But Sabine's answer is better because it makes sense. All right, so here's what I'd like to add to the conversation. If we look again at our diagram where we have C perpendicular to space. Now, I'm going to flatten it out in this visual just for clarity. The real answer here as to why the rocket ship is the one that experiences the time dilation and not the person on Earth is because the rocket ship is objectively at a different point on C than the person on Earth because it's a real dimension. So he has traveled farther down time than the person on Earth. He's experiencing less time, he's experiencing more space, and it's geometry. He moved. The acceleration, Sabine's right, acceleration is absolute. It's absolute because that's what actually changes your position between time and space. That's the answer. And again, since C is a mutually exclusive dimension of space, the more you travel through space, the less you travel through C. And this brings me to one of my biggest points, and I'm going to really drive this in. Perspective is not the same as reality. And that's the biggest thing that's gotten lost in our conversations on special relativity. And I know modern science is really uncomfortable with this kind of discernment. But the truth of the matter is, the person on Earth sees the rocket moving away 80% of light, and the person on the rocket, yes, can technically measure the person on Earth moving away from them at 80% speed of light, but there is an objective reality here. The person on Earth is right. By the way, as my daughter reminded me, there's not just two players in this situation, because if we're traveling through real space, the rocket ship wouldn't just see the Earth traveling away from it at 80% speed of light, it would see everything else in the universe traveling away from it at different relative speeds. And when you picture that, the absurdity of the paradox becomes even more clear. Moving on to what I think is an even more interesting question, why is the speed of light always observed traveling the same speed from all points of reference in special relativity? That's one of the other core factors of it. So to review this principle, with most things, acceleration adds onto our current speed. So let's imagine a person, and let's give him a potato cannon that can shoot a potato at about 100 miles an hour. And then we're going to take and put him in a car traveling about 30 miles per hour. To a stationary observer or victim, the potato would be traveling at 130 miles per hour when it was launched from the car. But now I'm going to take that same person in the car and I'm going to give him a flashlight. And now, instead of shooting potatoes, he's going to flash the flashlight as he travels towards the observer. What's going to happen is that no matter how fast that car goes, the light from that flashlight, every time he flashes it, is going to reach the observer at the same rate every time, at the speed of c. But here's where we get to the interesting part. While the light is going full speed, the car is still moving. So, by the time the light reaches the observer, the car will not be in the same position as the light makes it appear to be. Now, thankfully, relative to speed of light, cars move very, very slowly. Otherwise, this would be a big problem. If the car was going, say, 500,000 miles per hour, it might surprise the observer if he was trying to cross the street safely. So here's the thing we can learn from this understanding. Something traveling the speed of light itself, it's not that it doesn't experience any time, because remember, time is an experience, it's a comparison. So even though it's maxing out c, the only thing that changes is that everything moves relative to it. For example, if we went back to the illustration with Greenwich, and we move Greenwich all the way to the end so that she's at the very bottom of the time dimension, it is now the way she looks out on space, every single object is just moving different degrees slower than she is. Now, if you were actually in this situation, don't worry, you won't be, you would still have a sensation of time passing, because again, that's a function of memory. It would just look like everything's moving backwards. Doesn't mean time's going backwards. I want to be very specific about that. It's just that everything's moving relative to you now, and it's slower. I just really want to drive this home, because if we separate the experience of time from the physical property of time, there's no weird time stopping for light kind of stuff going on. It's still light. It exists with us in the world and present. That's why we can see it. And it still experiences a kind of relative motion. That's why even though light travels so incredibly fast, it still takes a while to get here from very distant galaxies, and why very distant galaxies still move when the light gets here, and we know that the light we're looking at is not where that galaxy still is because it's moved on since. So it's a change of perspective, but it's not some weird flow of time thing or time stopping. It's just C is the limit. And then the last thing I just want to call attention to a little bit here is that's also why we get things like length contraction. That's why we get some of those weird warping effects as you get closer to a higher percentage the speed of light. It's because things are moving after the light that hit them left, and so they start looking really weird as the light starts hitting your eyes with those weird kind of Doppler effects. So before we move on, let's dive into the math a bit so we can really break down how you can understand that it is a 90-degree angle, contradicular, so going a negative direction, to space, but yet that still somehow creates a hyperbolic path on time dilation as an object travels. So we're going to jump to that and go through it. All right, now we're going to do a deep dive into the math of time dilation. If you're new to the math, I'd like to think this is going to be a great way to kind of get familiar with it. If you're familiar with the math, this is going to seem probably incredibly basic at first, but bear with me because especially as we get into the conceptual breakdown, I think you're going to find some new things here. If you are, however, very impatient and you just want to get to the juicy stuff, feel free to skip this chapter, but please come back to it later, especially if you're skeptical, because a lot of the support for what I'm talking about is here. So that being said, let's move on. So keep in mind the way that we measure time, and specifically the way we quantify a second, is how long it takes time to travel the roughly 300 million meters that is the speed of C. So we usually do this with an apparatus where we have something emitting light. It's going to shine it across a distance, it's going to hit a mirror, reflect back, and then a sensor will read it on its return. We do this for a couple of reasons. We do this because, first of all, it makes sure that the clock reading the point at which time left and then returns is the same clock, which simplifies counting for different errors and problems. The other reason that we do this is because you have to measure light over a pretty long distance, so by having it go there and back again, it doubles the distance. But most importantly, we do this because it makes the math a lot easier. So it's practically required to make this work. We have to be able to cut distance in half. So, to be clear, we're starting this example with a stationary observer. He's standing next to the apparatus, and because he's not moving, he just sees light travel up and down, and then that's red. And the measurement gives him a sense of how much time has passed for him. And that forms our initial foundation or reference point, okay? Now, what we're gonna do is we're gonna compare him now to someone who's moving. So we're gonna take someone running, probably very quickly, and he's going to be running with the same apparatus. How he runs with that apparatus, I don't know. Let's just say it has wheels on it. Now, to the runner, since he's carrying the apparatus with him, light looks like it's still just going in a straight line. It's going up and down. But from our initial observer who's standing still, looking at the runner, light isn't moving up and down. Light is moving diagonally because now that light is having to move over space. So we represent that here with these two triangles. Now, as you know, Pythagorean theorem, c squared equals a squared plus b squared. Now, the c squared in Pythagorean theorem is not the c we've been talking about. That's just a variable here. But ironically, in this particular case, they will match up. So, as you can see, c forms the hypotenuse here of our two triangles. And that's our measure of time there that we had from the first observer. Now it's moving diagonally. The the velocity, now the amount of space he's moving over in this time frame, that forms the bottom here. And our distance up and down still stays the same because that's our original point of comparison. Everything is divided by 2 because we're breaking this up into two triangles. But when we get to our equation, you can see the very clear relationship to Pythagorean theorem. C squared now is our c squared here times time divided by 2. A squared is our d squared, and b squared is our velocity over time divided by 2. Right off the bat, this illustrates what I've been talking about of C being mutually exclusive, contradicular, and limited compared to space, because we're having to break it up into two triangles. It shows us how much we subtract from time as space increases. For comparison, if we were just solving a vector in space by itself, I could take, for example, the distance traveled in the y direction, the distance traveled in the x direction, just use the simplest form of Pythagorean theorem, and find the final vector. And that vector is equivalent to the hypotenuse of the triangle. But this is when the dimensions are perpendicular and not mutually exclusive. But in this particular case, that is what we're dealing with, so everything has to be now split. So this gives us the initial formation of our equation. And I'm not going to go through a whole proof, but I just want to connect the dots of how we get from there now to time dilation. So we take this and we move time out to the left. And as we can see, everything is still squared. And then we're going to go one final step here, and we're going to break out our original point of reference, 2d over c, and multiply that by what is now the Lorentz transformation. Now we have the square root built into the equation, so that what we finally calculate is just the time dilation of the person running. Now, what's really important to point out here is that we didn't necessarily have to take the time from our initial observer. We could just have the distance. That fits right into the equation right here. But what you usually see when we're talking about time dilation is you see this final form where we have the initial time compared to now the new time that is dilated. This often hides what's really going on here. Because if we had, for example, an absolute frame of reference, meaning we could measure time from a completely motionless point, we wouldn't even need necessarily to always pick an initial observer. We could just insert that in here as the original absolute reference, and then just measure the time difference of everything else compared to that. Now, I know if wishes were horses, right? But we're going to talk about later in this video how we could actually find an absolute frame of reference. The other thing I hope you've all appreciated is I took out the T0 and T1 and put in our little cute icons here. I'm actually personally just a little bit dyslexic, and those, anytime I'm comparing two things, it starts making my head hurt. So I find the pictures help and thought it'd help everyone else too. All right, so if C is a flat dimension, why is time dilation curved? And here I'm showing the graph that we've been using through most of the presentation. Well, here's why that is. Remember, when we're talking about dimensions, we could be talking about an object, meaning we're trying to figure out the shape of an object, or we could be talking about the surface of an object, the shape of the surface. We could be talking about the containing space, so the shape of the space the object is in. Or, and now here's the third thing, we could be talking about the path of an object. And in fact, most of the equations in physics are finding the path of an object. If we look back about what we just reviewed, at the beginning, when I outline and I show this shape here that we're using, I am showing the containing space. all of our assumptions as to how the universe is shaped is illustrated here. X, Y, and Z, they're flat, and they're shown with the straight line here for D and the straight line here for V. C is also straight, but it's mutually exclusive, so it forms a diagonal because we are taking away from it, okay? However, when we get to the final equation and what we're actually calculating here is the path of an object, specifically the runner. We are calculating his path through relative time and space. And that's just very important to keep in mind because those are very different things. And, to my next point, gradient forces produce curved paths of motion in flat space. So, if I hit a baseball, the moment my bat makes contact with the ball, I am exerting a straight force on that ball. But as the ball travels through space and time, it experiences other forces. It experiences gravity, which is a velocity gradient that causes the ball to accelerate downward. We have wind resistance, which is going against the ball, and that cumulatively adds up, slowing it down over time as well. If we chart the path of the ball on a graph, the path is curved, but the graph is what implies the shape of space. So we have the height of the ball over time, we get a curve, but the graph is flat. The graph is the containing space, the curve is the path of motion. And to really drive that point home, I can actually just swap out height and time with height and distance. And I'll get pretty much the same graph, just comparing the ball's height over the length of the field it is traveling. I don't even need time. They're interchangeable, okay? And that's the point. To drive this home, here I have a unit circle, okay? If time and space form a mutually exclusive relationship, the more you travel through time, the less you travel through space, and vice versa. As you can see, though, that produces a curve, because just like in a circle here, if I start perfectly motionless, I'm just going to be on this x-axis. And then the more I travel through space, you will see that I go down on this x-axis and up on this y-axis. And this relationship of being mutually exclusive produces then a curve. Now, keep in mind, I'm showing this on a two-dimensional circle, and as we've already talked about, that's not an accurate representation. This is actually a 4D circle, but all of my 3 dimensions of space are just being, flattened here. So just keep in mind the proportion or the curve here is off. I'm just trying to make a point as to the nature of the relationship. Time dilation, what we're actually calculating with time dilation is the tangent wave of a path that it experiences as it's traveling through time and space. To show you that, here is what a tangent wave looks like for a normal 2D unit circle, and here is time dilation. And as you can see, the trigonometric function here, we have that here for the tangent. Here is a 4-dimensional tangent wave, which gives you the same result as our time dilation equation. So even though in 4 dimensions our tangent wave is stretched out like this, the curve is the same. So the 4-dimensional curve is charting the amount of time dilation an object experiences as it accelerates. What I've been using in my little Minkowski spacetime diagram here is I've just been inverting that, because instead of representing the amount of time dilation, I'm showing the effect of it in the end, which implies its position relative to time and space. So that's why I've been using this graph this whole time instead of this one. So is C a circle? Am I saying that time is a circle? No, because if we go back to our unit circle here, we can see that I only have a fourth of the circle. We don't have the rest of this. We haven't observed anything in physics that lets us know there's anything going in any of these directions. We just have this relationship, and it happens to be a curve. Now, there's a chance, or let me put it a different way. Right now, we are assuming that time is just contradicular to space, which inherently gives us this relationship. In order for there to be a circle here, or like an actual circle, it would have to be some other dimension that is constraining these into this relationship, and we're not there right now. Also, just keep in mind that when we chart time dilation, we're charting that with the assumption of consistent acceleration. So, this is consistent acceleration applied as an object moves through time and space, but that's not necessarily how something has to move. If we had a really cool spaceship that could just jump between these different speeds, it would just form dots. So it's just important to keep in mind how deceptive some of these graphs and charts can be, because there's a lot of assumptions built in. We're not always saying what it is we're representing visually. And again, a lot of these curves, they only exist when we're plotting things in consistent gradients. So the curved relationship of C to traditional space is a consequence of a contradicular relationship between flat dimensions and the fact that C is limited. Now, is this a math proof? No, I don't. Again, I don't necessarily think the math right now has the language for this. Conceptually speaking, though, I feel it's pretty solid evidence. It's at least as solid as set theory. All right, caveat though. I am not excluding the possibility that the universe as an overall shape is a very strange looking high dimensional sphere, but I'm also not saying that's true either right now. Just basically think of it this way. If this idea helps you process this information, feel free to take it. If it's confusing, just pass it by. All right. If C is just a geometric dimension, if it really is the same thing as space, it's just contradicular, why can't we measure it in the same units as space? Well, we already do. This chart is from the National Institute of Standards and Technology. This is what we use to create a standard for all of our measurements. And as you can see, in the end, everything we measure is eventually at some point drawn back to time. And the reason for this, time, C, it's drawn back to C here. The reason for this is because c is the only thing we have an absolute of. Since c is always the same, then it forms a foundation by which we can compare everything to. So we measure a second by how long it takes light to travel, the roughly 300 million meters, and we measure a meter by how long light traveled in 1 over 300 million meters a second. And if you see a problem there, you're not wrong. It means you're paying attention. To really drive this home, I'm going to show a couple things here. So one of my commenters, I have his YouTube user up here. His first name's Casey. Good luck on the second part. But he reached out pointing out this scientific study that got a lot of headlines for a while, where people are postulating the idea of space as 3 dimensions of time, 1 dimension of space. Now, the headlines for this study were, scientists think space might be, 1 dimension of space, 3 of time. That's not really the point of the article. It was more an exploration of causality when things are traveling faster than light. But that's neither here nor there. The point is that it shows a lot of our equations of special relativity rewritten with this flip. And sure, of course we can. Of course we can do that. There's no difference in representing space as with time as our standard dimension, and then all 3 dimensions of space being contradicular to that, or having all 3 dimensions of space with time being contradicular to those. Either way, you get the same results. That's the point. They're all the same thing. Another point to drive this home is another follower of mine on Twitter. His name's Archmichael. I have his Twitter handle here. He regularly posts what I can only describe as physics graffiti. It's these wonderful little one-off thoughts he just throws out into the universe here, where he is constantly mixing up different forms of measurement and comparisons and equations, relating them to other things. And, the truth is they vary between what I would consider silly correlations to insightful connections to, frankly, profound paradigm shifts. What's really amusing to me is how hard it is to tell the difference between the first and the latter. But the point is, he's playing around, right? He's playing around with physics. I think it's a wonderful example. It's always good to, shake up your neurons a bit. He's a very pleasant fellow. I know a lot of us crackpot physicists get a reputation for being abrasive, if not outright scary. This guy is just full of positive energy and good vibes, and he's just playing around. And I just think that's wonderful. Frankly, I think he's setting a good example for the physics community as a whole, because we should be able to explore absurd ideas from time to time without always having to be sure they're 100% true or not, because that's the point, is to play around. When I get frustrated with science journalism and stuff is when we throw out a crazy idea, but we throw that crazy idea out as if it's somehow superior to everyone else's crazy ideas. And, that's where I feel like science culturally becomes prohibitive. All right, but with that in mind, here's the thing. A lot of people got hung up on my first video, and probably still sticking here, on the idea of, they can't be the same thing. We measure 1 through time and we measure other through meters. But an SI unit does not define what a thing is. It only defines what we measure something relative to. So, for example, we measure velocity relative to meters and seconds. Heck, we measure gravity relative to 3 spatial dimensions, weight, and 2 measurements of time. So what the hell is that, right? By the way, I answered that in my first video. But the point is, just because we have an SI unit for something does not mean that defines what the thing is. And so people need to get over that and just realize that the only thing an SI unit identifies is what we're measuring something compared to, right? All right, so going through all of this, what's the big hang-up? What's the real problem with the way I'm representing C versus our current understanding of special and general relativity? Well, the big hang-up is special relativity currently postulates that there is no absolute frames of reference. I've talked about this already a bit, but that's the thing. Scientists have this idea that everything's relative, everything's equally valid, there's no absolute frame of reference. So for C to be accepted as a containing dimension, it must have an absolute point of zero velocity that we can compare everything to. And if you're thinking, well, that seems like an impossible thing then to find, then you need to stay tuned for the rest of the video, because that's exactly what I'm going to show how to do. So obviously in my first video, I definitely made some mistakes, typos, things like that. But of all of the contradictions or errors, the YouTube commenters were more than excited to point out. There was one I left in on purpose that no one caught. So I actually contradicted myself in the last video. So if you go back, I say this about space-time. We can stop calling it space-time. I think that's one of the most confusing parts of this whole thing, is by calling it space-time, we're just admitting, time is changing, something weird's happening with space, we don't know what. With a fourth dimension of space that we acknowledge, it can just be space and time. And then at the end of my video, I said this. In the meantime, you can look forward to my next chapter, which is going to be time as a spatial dimension. I left that in on purpose because I wanted to correct it now. Because as you can see, I've actually kind of made both true. So I am trying to separate time and space in terms of flexibility, because that's the biggest problem we have with general relativity right now. We see space-time bending, and that's what I want to get rid of. And we're going to move on a little bit here to that. However, I am also making the case for time as being a physical dimension of the universe that we're in, and that we're actually moving through it. So depending on your wording, I kind of got us back to space-time, but at the same time, I've broken apart the space-time that we had. I just really wanted to cover this because that is one of the challenges of this whole thing. And the truth is, as I move on and as we continue to stack concepts on each other, something I say now is going to be true with the context it has, and then as we add more context later, it's going to change again. I'm sorry, that's the best I can do. To review, what we've been calling time in physics is actually just C. And most of the things that we put onto time, those are other ideas, mental, cultural, other things. All right, so we're going to move into some new and exciting ideas here, but let's just stop for a minute, do a quick review of what we learned, because I need to keep this all in context. The dimension of C is unique in both direction and size. So compared to all the other dimensions that we're familiar with and we approve of, time is both limited as compared to infinite, and it's pointing in a negative direction. By acknowledging C as a physical dimension or part of the shape of the universe, we can explain inertia as simply standing still relative to C in space. An object in motion stays in motion because, in fact, it's not moving along the C dimension, and everything else is just at a different point on C, so it gives this appearance of relative motion. We can now understand why it takes energy to accelerate, but not necessarily energy to stay in motion in the vacuum of space, because acceleration is actually what causes change. I want to take a little time at this point and discuss all the objections scientists have to this idea of looking at time as a physical dimension. That was one of the things people asked me to do in my last video, and I think it's a great idea to look at, to just say, here's all the problems. So for a lot of you, this might be really boring, and for a lot of you, it may be really interesting. So please feel free to skip ahead a chapter. I do have my chapter markers down there. And for those of you that don't care, I'll see you on the other side. So let me cover a few reasons why this way of thinking about time isn't more common right now. So the first one, and I just can't say this enough, Scientists have the same problem with semantics that we do. They're still people just like us, mostly. And they are also confusing all the different ideas of time with what we're actually measuring in physics, which is c. So that's just a normal human problem. Another problem is that in a what I would call desperate effort to quantify some of these ideas of time, we've come up with some pretty strange ways of validating it. The first one is entropy. And I find that incredibly specious to say that entropy is proof that time flows forward. Because again, it's a system. Now, it's predictable, but first of all, it's under debate whether it's universal. Not in the thermodynamic sense. In that sense, it's definitely universal, but applying it as a broader philosophical concept to everything, it's a bit of a stretch. And because depending on where you look, it's defined as either the measure of work a system is capable of, in which case every system moves from being able to do work to not doing work. And that, to me, is a good definition for entropy. It's a very mechanical one. But the other one, which is entropy as a measure of order moving to chaos, well, that's where we start digging into philosophy. And again, I would argue that in many ways that's still an emergent concept. Now, it's a pattern, it's a predictable pattern that we find in nature. But outside of heat dispersion, energy distribution, and those kind of things, it becomes more and more complicated to apply it on a universal plateau. So I'm definitely going to say emergent concept on that one. And even then, not sure that's really a good way to say that's proof time moves forward. Another big reason science doesn't teach time this way is because one of the main postulates of special relativity is that idea that there is no absolute frame of reference. So if there's no absolute frame of reference, then there is no objective way to judge one frame of reference as more valid than another. But we've already just shown, not just me, but Don and Sabine Hassenfelder have shown that you have to find some way to make an objective judgment of one point of view being more relative to another, or it just doesn't work. So I think the assumption that there is no absolute frame of reference is also shaky. And I'm actually going to show later how we can prove that there is an absolute point. In one of his videos, which I've linked to in the description, Arvin Ash does a great job of showing Minkowski spacetime and how it changes the way events are perceived depending on your point of reference. In this particular clip, which I'm just going to go ahead and show a little bit of, he shows a light going off between two sensors, and the sensors are equal distance from the light. So they both turn on at the same time. However, to a third-person perspective, moving at a different speed relative to the system, he is going to observe the light going off in the middle and the sensor on one side turning on before the other. What Arvin fails to discuss in this example is that the observer is wrong. The light is hitting both sensors at the same time. It just takes the light from one of the sensors longer to reach the observer because of the angle and speed that they're at. But just because it takes them longer to see it doesn't mean it didn't happen. And to be clear, I really like Arvin, and he does an amazing job of explaining science concepts in this video. This is just something I'm bothered about with the community in general, and he just did a great job of showing the thing that frustrates me so much. The other reason scientists don't talk about time this way is because, like I said, they kind of have everything mixed together, so they have to stick to this idea of time, space-time curving. And this is why I've talked so much in this video about discerning between the containing space and the path of an object, or the object itself. And it's also why I did my last video on gravity as a fourth spatial dimension first before doing this one. Because you have to break out a fourth spatial dimension in order for C as time to stay constant. Otherwise, time's doing this weird warping thing and changing all the time, as opposed to the relative distance between 2 points changing. If everything about what I just said was very confusing to you, please go back and watch the first chapter in the series. What we currently think of as space-time curving is not space changing. It is the path of an object changing. The containing space remains consistent. The W dimension I added in the last video is just a fourth spatial dimension that adds additional distance objects have to travel, which curves the path of an object. So again, the math stays the same. It's how we interpret and discern what we are looking at that matters. One more point. Scientists really hate extra dimensions. I don't know why, they just do. If there's anything I've learned going through this series and reading the history of where all these things came from, damn, scientists really just hate extra dimensions. As a matter of fact, Maxwell's equations originally started out using quaternions, which I'm not getting into just yet. And scientists hated the implication so much because those are equations that discuss four-dimensional rotation that they rewrote them to remove the idea. But for some reason, they really love the multiverse. And now, of course, scientists really also don't like conditional dimensions. The nice parts about X, Y, and Z is that they're infinite, unchanging, and just always the same in every equation. C being limited has already caused trouble that frustrates us, and W, as I proposed in my last video, is really despised because it is a dimension that is not always being interacted with. It is a conditional dimension. Sometimes objects interact with it, sometimes they don't. So that is also confusing, and they don't like it. It makes the equations very complicated. Also, scientists really like the Big Bang. They love the Big Bang. It's great. It's like their little baby. They're going to keep it, they're going to protect it, they're going to take care of it. And I'm not just saying this. There was an article recently put out on Big Think that basically says any theory that causes scientists to have to rethink the Big Bang is typically poo-pooed right away. I have an idea. Why don't we plug all the holes in physics before we assume we know how the universe started? Just a thought. The truth of the matter is, as much as scientists claim to be objective empiricists, there's always a little bit of religion and everything left over from humanity no matter what. Another point. We lack a good mathematical language to discuss extra dimensions. I think that's been one of my biggest struggles I've been going through this process because I keep looking under sofa cushions and dusty old textbooks thinking it's got to be there somewhere. A lot of people have thrown out differential geometry to me and other ideas, but I'm just going to be honest, they're sometimes helpful, but they just don't cut it. Partly because of what I've been talking with hyperbola and hyperbolic curves. In order to make extra dimensions seem understandable, we turn them into lower dimensional equations, which causes some really weird shapes. And what I'm learning is that while there is an initial understanding that that's what we're doing, we then seem to fail to kind of like backwards interpret what we're looking at to the idea of the original containing space we were trying to understand. And that's where we end up creating weird things like quantum manifolds and stuff like that. The other weird conception in extra-dimensional geometry I'm unsatisfied with is the idea of projection. And we showed you this earlier with the idea of taking the Earth and flattening it out into a map. Again, I'm not saying it's not useful, and I have actually found a few examples, I think, moving forward where it will be useful, but it's not the whole picture because, as we showed in one of my previous dimensional concepts, a higher dimension intersecting with a lower dimension creates more of a temporary effect, a phenomenon that is observed and then gone. And because that's what it's doing, it's passing through the lower dimension. We don't have a lot of good math for what a higher dimension looks like passing through a lower one. The only time you're going to see a higher dimension projected onto a lower one is if it's splattering on it like a floor. So if I take my poor three-dimensional ball from the original example and smash it on the floor, now it's projected. Now, several of my commenters brought to my attention the idea of quaternions And I have to admit, I absolutely love that a lot. Apparently, I really don't want to get too much into it now because it's going to be a big part of my next chapter. But bottom line is, it's an equation that can be used for four-dimensional rotation. And what I like about that is rotation is indicative of the containing space that an object is in. So there's no distortion, there's no warping. You're representing the turns and the rotation accurately. Of course, if we try to visualize it, then we're back to projection. But really excited about that one. Stay tuned for the next chapter. So now that we have all that out of the way, let's move forward. If the idea I'm proposing is correct, what are the consequences? What does that mean for how we understand the universe? So the first question it answers is, why does time move forward? Why does the arrow of time always move forward and never backwards? Well, the answer to that is really simple. Time doesn't move forward. Time doesn't move. Objects move relative to time. It's just a side of the universe. It's just there, and we move relative to it. There's no forward or back going on here. It's like asking me in the vacuum of space which way is up. There is no up. There's no down. You're just moving. That's it. Everything's relative to everything else. So time can never go backwards because time's never going forward. We're just all here. All right, so if we understand that concept, the next question becomes quite obvious. Is time travel possible? No. There's nowhere to travel to. What are you doing? Where are you going? No, there's nowhere to go. Look, I know, it's a downer. But at least you can still be bigger on the inside.
You have to imagine a very big box fitting inside a very small box.
It also means that relative motion is the only physical, observable phenomenon that we can categorize as time in physics, or see. Again, that's it. That's what it is. It's relative motion. That's what we're observing. Everything else is an experience that's just central to being a human being. All those other aspects, history, memory, waste of time, all those things, these are emotions, they're feelings, they're how we process the world around us. They're emergent properties. There is no scientific evidence of the universe having the past stored somewhere that we can go to, or knowing the future that we can jump to, outside of variables and patterns and physical consequences. Another consequence of understanding time as, again, another side of the universe, but a limited side, is that we now know time does not flow backwards in a black hole. As I said in my last video, it just stops. It just stops. Everything is frozen in the black hole because you've reached the edge of C. And I just can't harp on enough how many of these ideas don't really come from math or physics we observe. It comes from weird interpretations and assumptions that we make. The only reason so many scientists think time goes backwards in a black hole is because they just ask themselves, what if I draw this line past the edge of the graph? And let's be clear that it's true when I represent something in the physical world on a graph. It's very easy for me with a pencil to draw that trend line past the axis. But we have to ask ourselves, is that axis passable? Here's an example. So let's imagine a little guy on top of a building, and he's going to jump off the building. Don't worry, no cartoon characters were harmed here. These are professionals. As he jumps off the building, he accelerates and then hits the ground. Now, I can graph his change in height over time, and it will look very similar to what we just saw. And I can put this on a graph, but just because I put it on a graph doesn't mean I can't draw the line past it. That would be very weird. He would just fall off the building, and then he would just keep falling, and then we'd get into infinities, and we'd be all back in the mess of where we are. Now, it may seem like I'm almost being insultingly simple here. And I'm sorry, but the truth of the matter is scientists do this all the time. So let me just show you a few clips from this PBS Spacetime video.
As we take this journey, we're also going to plot our path on the Penrose diagram. When we first enter the Kerr black hole, we find it's just like every non-rotating Spacial black hole we've ever visited. Down becomes the future because falling space drags us there faster than the speed of light. Space and time switch places. Now, as we fall, the outward pressure due to the black hole's rotation starts to win against that inward flow. In fact, the flow eventually slows to less than the speed of light. This leads to a second event horizon called the inner horizon. On the other side, space and time switch back to their proper order. You're now free to not fall, so you can jet around and explore the interior. Below you is the black hole singularity, but it looks odd. The singular central point has been spun out into a ring of infinite density. It's surrounded by a second ergosphere, where again the rotational flow of space exceeds light speed. So what next?
Okay, what he used in that video was a Penrose graph. And just so you know, that's just another way of showing the Minkowski spacetime. Just again, from another perspective. It's the same thing we've been covering. The assumption made in that video was you just take the graph and you just keep drawing the line. You just keep stacking it on each other and it just keeps going and going forever. Why? We have nothing, we have seen nothing, we have observed nothing that leads us to believe we should do that. And yet, this idea, this kind of multiverse way of thinking about black holes has become pervasive in science journalism right now. It's a distraction and it's confusing from what we could actually understand about our world. If C is part of the side of the shape of the universe and it's limited, then that means it stops. The graph stops and you hit the floor. That's why I said the most reasonable assumption about what's inside of a black hole is whatever was there when it formed, just frozen. The gravity grew so intense that it formed that radius, the event horizon around the black hole, and now everything inside it is just stopped. And I might go into this in a future video, but that's why black holes spit stuff out. Gamma radiation is caused by stars exploding, and stars exploding cause a lot of gravity. If it caused enough to freeze them inside of a black hole, then they're gonna leak out. Kind of like how ice melts and refreezes throughout a year. The edge of a black hole is not stable because it's based on very, very powerful physics, and it's always a little bit in flux based on mass coming in and how it moves. So that explains what we're seeing. What we're not seeing is a portal to another universe. Okay, and I know it sounds like I'm being harsh here, but this is what I gotta say. This PBS video, Spacetime video, made me so angry. It's part of what actually got me to get up and do this whole thing. So at the very least, I can say thank you for inspiring me to spend what has now been, I think, at least 18 months just doing this, because this video just really put me over the top. If this is what the real scientists are throwing around these days, I have no shame coming on here as, you know, an amateur and trying to propose something that I think is very reasonable. Another thing this means, if we understand time or see this way, is that wormholes don't exist. Wormholes are created by the idea, again, of space-time curving in and another point in space-time curving in and those points connecting. Wormholes and black holes are pretty much the same thing, just wormholes are two black holes connected. But again, as I said, if you saw my first video, I describe gravity not as a bowling ball on a trampoline, pulling space down, but actually as mass displacing fourth dimensional space, kind of like a bowling ball in Jello. This means a black hole is basically a bunch of mass pushing fourth dimensional space to a point where c can't be passed around the edge. With this understanding, there's no hole. It's a bump. It's a black bump. So there's no wormhole. So when we separate out a fourth spatial dimension, we have c as the side of space. The only thing curving is the path of objects. Now, if you're not already familiar, take the explanation of time that I've given in this video, and I greatly encourage you to go look up the official explanations. I have linked to a bunch of videos in the description of real scientists, prestigious academic experts, all the big names talking about what they think time is. Please compare their explanations to this. I will take that contest any day. Okay, I hear you, Chris. You're getting a little bit cocky. There's definitely a little bit of passion here, I admit. But can this concept of time, as the idea of c being a physical side of the universe, of the containing space, can this be proven? Yes. Not only can we prove this idea of time, but we can find the absolute reference point of the universe, true zero velocity. Here's how it works. First, understand that we have only so far measured light, the speed of light, in a straight line. We typically shine a laser over a large distance and reflect it back and see how long it took. Now, there are a lot of inherent problems with the way we measure time, and the truth of the matter is what we measure does change a little bit. We don't like talking about it. There's a good video from Veritasium that I put in the description that kind of talks about how we've never truly measured the speed of light. So that's an enjoyable thing to look for, hopefully, after you finish this one. We're going to fix that with something very similar to what's called a Dyson sphere.
A Dyson sphere? It's a very old theory, number one. I'm not surprised that you haven't heard of it. In the 20th century, a physicist called Freeman Dyson postulated the theory that an enormous hollow sphere could be constructed around a star. This would have the advantage of harnessing all the radiant energy of that star, and any population living on the interior surface would have virtually inexhaustible sources of power.
However, in this case, we're going to build something much smaller, and the point isn't to collect energy, the point is to measure light. We build a vacuum-sealed sphere. The inside of the surface of the sphere is covered with evenly spaced sensors, and at the center of the sphere is a light source. A burst of light is emitted from the center, and each sensor measures when the light reaches that sensor. Now, the size of the sphere would depend on the sensitivity of our instruments. I estimate it would have to have a radius of maybe 1 kilometer at least, maybe more. When we run the experiment, the light from the middle will hit each sensor around the edge of the sphere at a slightly different time. And it's going to do that because even if it was just stationary on the Earth itself is moving at about an estimated 2,300 meters per second, just relative to things we can observe in the galaxy. That's about 0.0768% the speed of light. So because of that, and again, going back to the car illustration that we did earlier, the light will always have a consistent speed, but everything moves relative to the light. This experiment right away gives us 2 data points to compare. We have the shape of the sphere, but then we have the shape of the light emitted from the center as it hit the sensors. The sphere that we calculate from when the light hits the sensors is always going to be warped compared to the shape of the physical sphere. The difference between these two spheres allows us to understand which direction we are moving relative to a point of absolute zero velocity. Now, doing this once teaches us almost nothing. It would take running this thing kind of like we do the Hadron Collider, where we capture millions of readings over a long period of time. Just testing it out over and over again. By doing this, we would have enough data to work out all the different ways the light sphere moves relative to the physical sphere. And eventually, that would help us average out the direction in which Earth is moving to relative to zero velocity. So, doing this experiment would help us accomplish two big things. First of all, it would give us a better measurement for the speed of light, because instead of just measuring light in one direction, in one frame of reference, we'd be measuring light millions of times from an entire sphere of different angles to compensate for all the different things that change the measurement. After all, when it's nearly impossible to measure something precisely once, the way we fix that in science is by measuring it a whole lot. The other thing that this experiment would allow us to do is it would allow us to discover the direction of true zero. In other words, what the Earth is moving ultimately relative to in the universe. Even though the Earth is spinning and it's going around the sun, and the sun's going around, and the solar system's going around the galaxy, by collecting millions and millions of snapshots over time, we would be able to average out what the actual vector is that we're moving away from in reference to absolute zero. As a final step, once we calculate the direction of true zero, we send out a rocket ship, unmanned, I guess technically more like a probe. If this theory is true, the clocks on that rocket ship would actually end up moving faster. Because while the rocket ship would appear to be moving faster to us, relative to the universe, it's actually slamming on the brakes. I realize that this would be a big undertaking. Obviously, I can't do it myself. However, I believe it would be a lot less expensive than our colliders. Probably the most expensive part would be the rocket, or there's also the chance we'd have to put the sphere in space, depending on the size. But I believe what it would teach us about our universe would be well worth the effort. This would allow us to find the absolute reference point for C, so that we knew at which point we are already starting out along the line of that dimension. And this would allow us to update the way that we calculate relative time and motion, because we would be able to measure time in absolute distance the same way we try to measure length, width, and height. As a side note, the fact that we are traveling at least 0.0768% of C is why it doesn't faze me when those science journalism articles come out saying, oh, we may have measured neutrinos going a little faster than the speed of light. Well, I mean, if that's true, that's bound to happen. Wake me up when something travels past 0.1% the speed of light. Now, I've been touting common sense for this video. Let me play a little crazy for a little bit. For a lot of you, it may seem like this entire idea takes all the fun out of theoretical physics. I've destroyed the multiverse, and I've destroyed time travel. So let me give you a couple presents back. Anti-gravity and faster than light travel. First, let's redefine anti-gravity. It does not mean falling up, and it's not a repelling force. Just like we covered in the first video, gravity is not really a force. It's an effect of fourth dimensional space becoming more compact between two three-dimensional points. So, anti-gravity then would be the shrinking of fourth dimensional distance between two three-dimensional points. In other words, if we made a teeny tiny anti-gravity field on Earth, things wouldn't fall up, they would just get a little lighter. You would have to cancel out the entire effect of Earth's gravity before something would appear to be somewhat falling up. And even then, it would kind of go in an anti-orbit. So I added a asterisk to my W dimension earlier. Let me explain why. So if I go back to the graph we used to kind of summarize what we're doing with Minkowski spacetime, time is contradicular to all the dimensions of space, but all the dimensions of space, they're perpendicular to each other, which means they're additive. So when we're comparing them, we can actually compress them all together into the x-axis, with time being perpendicular on a two-dimensional axis. So I included W in that originally, but that's because I was only including W in one direction. Again, logically speaking, if we can displace and compress W, then that means we can stretch it, which means in one direction, W adds to the distance of x, y, and z in relationship to time, but in the other direction, it subtracts. And by the way, I'll give you a moment of self-awareness that I am making the exact same sin right now that I just made fun of PBS for. I am drawing a line past the graph. So I want to say, as we move forward into my future chapters, I understand that I definitely have to validate how that can be true and by what measure we would do that. So if we can stretch fourth dimensional space and reduce the fourth dimensional distance between two three-dimensional points, then that means, theoretically, there exists possibility that you can reduce that distance to zero. With zero expression of energy between two three-dimensional points, there is no interaction with C. So there's nothing stopping you from traveling the speed of C or faster because you've actually left it altogether. It's kind of like a cube where you just travel along one side and forget one of the dimensions entirely. This means not only can we achieve that faster light travel, but we can do it without worrying about time dilation. There'd still be a little bit of a difference, but it wouldn't be that drastic, Close Encounters of the Third Kind, where you go travel faster speed of light and come back to Earth in the future. It would be more negligible difference in time as you're traveling in the ship compared to the people on Earth, if any. So faster than light travel is achieved not by going faster than C, but by actually geometrically avoiding it altogether. This is what I believe is a more accurate description of what we often call folding space. The current idea of warp drive is based very similar on the same ideas we have with the wormhole. It's the idea that space-time is curved. And so you have to create a ship where you're basically warping space in both directions, one in front, one behind, and you're kind of surfing a wave of curved space-time. This would require a massive amount of energy, which is obviously immediately prohibitive, but again, it's based on the same logic of a wormhole where we start imagining space as folding a piece of paper. In reality, what faster than light travel means under this idea is that instead of trying to create a wormhole, or instead of trying to surf along the curve of space-time, you would actually be creating a slipstream. You would just be stretching fourth dimensional space on both sides of your ship, and you don't even have to stretch it that far away, just a little bit, to keep you out, to have a time factor of zero as you travel. So where do we go from here? So the big question now is, if matter causes the displacement of fourth dimensional space, why? How? That's definitely on me to answer right now. When I answer that, and please forgive the hubris of saying when, we'll know how to stretch it at the same time. This is why I haven't spent a lot of time reworking general relativity and arguing about the math on that, not only because other people have already done that, trying to rework it into 5 dimensions, but because it's kind of moving the deck chairs around. This argument was already lost back when Einstein was first trying to find the best way to formulate his theory. And if there's anything I've learned about the scientific community at this point, they're not going to change any of their ideas about anything unless it's hit with a blunt hammer. As a side note, the James Webb Telescope has been chipping away at it pretty heavily, and they're still clinging on for dear life. The truth of the matter is there's lots of different ways to write general relativity where the math still adds up at the end. It's just not a strong enough argument. What I'd rather do is just kind of keep moving forward. I have proposed 2 experiments so far. In the follow-up video to my last one, I said if we can build a giant computer model of the entire galaxy and be able to calculate overlapping fields with a little bit of work on fluid dynamics, then we could start factoring in the interaction of cumulative displaced gravitational fields over time. And now I've proposed the quote-unquote Dyson sphere idea. The problem with both of these ideas is that they require a lot of money and resources, and so no one's probably going to do those. So the point of this whole project, when we get to the end of it, my plan is to rework and simplify the standard model. Because whereas 5-dimension makes general relativity more complicated, you can't make the standard model more mathematically complicated. I will definitely be able to simplify that. And we're going to do that by bringing the principles of general relativity over into the subatomic world. Second, I'm going to produce another suggestion for a practical and testable anti-gravity experiment. I'm not ready to say anything, but that might actually bring up a couple other fun things to do. And just to clarify, I am not going to be showing you a faster-than-light engine. I'm not an engineer. It's going to be more like how this equation enabled us to invent airplanes. So just setting good expectations there. I'm considering 2 follow-up videos. I was thinking of doing a really in-depth nerd video on the math of black holes and going more in depth on how these ideas change the way we approach it. And the other one I'm thinking of doing is a video on conceptual math in relationship to extra-dimensional mathematics, so covering things like differential geometry and quaternions. However, every time I stop to do one of those, it's going to take me longer to do my next video. So I would appreciate your feedback. If you think I need to stop and go a little more depth on those topics before I move forward, I'll hear you out. But if you guys think I should just keep moving on, I would appreciate some feedback there. Now look, several people pointed out to me in the first video that Clues the Client already tried to explain gravity with 5 dimensions. I also pointed that out, so I'm not really sure why they felt they needed to. However, what if I told you that good old Theodore Kaluza, when trying to explain general relativity with an extra dimension, did in fact do a pretty good job of discovering an extra dimension. It just wasn't gravity. Also, going back to what I said before about concepts kind of changing as we go, and may seem a little contradictory, I just spent this whole thing talking about C, but for those in the know, we know that C actually looks like this. So, I hope you'll all stick around and be patient for the next chapter as we take these dimensional concepts and now bring them into the world of electromagnetism, or as I like to title it,
Fucking magnets, how do they work?